In this video, we're continuing Chapter 8 of Price Analysis, a fundamental approach to the study of commodity prices. So we just finished talking about how you might go about making expectations about forecasting planted acres. But if you notice in Figure 1, when we're calculating the yield, we should be forecasting the yield per harvested acre, not yield per planted acre. And that is a kind of an important difference because every year there's a certain number of acres that are abandoned or harvested for silage instead of harvested for grain. And we're not going to be able to calculate those acres in our yield estimates. So we have to translate our estimate for area planted into an area harvested estimate. Coming back down here to the forecasting harvested acres section, we'll talk about how we can go about doing that. So in Figure 5, I've got planted here historical corn planted acres and historical harvested acres from 2000 to 2014. I've also graphed the difference between these two lines, and that is represented on the right-hand axis, whereas the planted acres and harvested acres are represented on the left y-axis. Now notice the difference between planted acres and harvested acres is actually pretty stable. It averages 7.6 million acres during this time frame, and you can only see two real big spikes up. And that you might not be surprised to realize that actually corresponds to two significant drought years during that sample. The most recent being 2012, and then 2002 was also a drought year. Now, why would you get an increased difference between planted acres and harvested acres in a drought year? Well, some of the difference between those two measures comes from acres that are abandoned, and they're not abandoned. You would never abandon acres if it's going to be profitable to harvest it. You only abandon acres when it would cost you more to run the combine and get it out of the field than you would actually earn from selling the grain. And that happens on on more acres than usual in dry and hot years like drought years. So you'll always see a little uptick in this difference between acres planted and acres harvested. But when we're talking about the pre-growing season, if we're trying to come up with estimates for our balance sheet, we can be pretty safe in just estimating our harvested acres number to be about 7.5 million acres less than our planted acres number. And then as we go into the growing season, if it happens to be a dry year where we're going to have realized yields significantly below trend, then we might think about estimating or revising downward our estimate for harvested acres relative to our estimate for planted acres. That puts us in pretty good shape in terms of coming up with a forecast for planted acres and harvested acres. The next step towards forecasting production then is to forecast yield per harvested acre in the balance sheet. Prior to the summer growing season, our best estimate of yield is just going to be to plug in whatever the trend yield is. And so let's talk a little bit about estimating trend yields for corn. Now, it turns out that the USDA has records on crop yields, especially corn yields, that go back to 1866, which is quite a while in the history. When you plot those yields, though, you can start to see that those older yield realizations are probably not that useful for estimating what current trend yields would be. If you fit a line through that curve, you just get a really bad approximation about what the next realization in the series will be. Now, this yield line has a really hockey stick-like shape because in the 1940s and into the 50s, we had some really wonderful advancements in the development of hybrid seeds that allowed crop yields to really explode as the seed varieties were becoming more drought tolerant and more resistant to pests and other things. And then as we got into more recent times, we saw those same kind of yield advantages being brought about by advances in genetic engineering and other biotech technologies. So that curve has been on a really steep upward trend ever since the 1950s. In forecast speak, you would talk about a drastic change like that as a structural change or a structural break. And what that means is the environment has changed so much that you might as well throw away the old data and not use it for forecasting because it's just not going to be helpful to you anymore. And we'll see that that's really what we're going to end up doing. So we know we need to throw away that old data before the structural break, but it's not exactly clear when the structural break happened or when we should sort of start including data in our sample to estimate a trend yield. The nice thing is that it turns out that it doesn't matter a whole lot where you break the sample because that trend line has been so consistent over time. To illustrate this point, I've plotted the yield realizations in two graphs. The first one on top is from 1952 to 2016, and then I put a trend line through that and got this equation here. And then I broke the sample much more recently in 1980 and put a trend line through that. And you'll notice that those trend lines are very, very similar, and they indicate that yields are growing at approximately a rate of just under 2 bushels per year. And we get that answer whether we break the sample in 1952 or whether we break the sample in 1980. So pick your pleasure. You're not going to get very different answers in either case. In fact, we can see that really drastically if we plug in 2015 into our yield equation with the first estimate when we included 1952 to 2016 in our sample. The trend line or the trend yield for that is 163.9. And if we plug 2015 into the second trend yield where we broke the sample in 1980, we get 162.83. So very similar estimates for trend yield no matter where we break it. So trend yields are useful for coming up with a yield estimate prior to the growing season, but once we get into May, June, and July, we have more information than that. We know if it's been a wet year, we know if it's been a dry year, and we can revise our estimates to come up with a more intelligent or more accurate estimate of what we think yields are going to be. And the USDA does the same. So prior to August, they don't have a way to go out and actually measure what yields will be, or at least they don't employ a method like that prior to August. But they do what they call the Agricultural Yield Survey. And that's where they basically send a survey out to a large number of farmers and just ask them to estimate yield. And that's just basically what they can do prior to when they can go out and measure pod counts and plant populations and number of ears per plant and all kinds of stuff that they can use once the crop is a little bit more mature. August, however, is the first month when they do start doing that stuff, and it's called the Objective Yield Survey. And so they send agronomists out to a large number of fields, and they make actual estimates based on count of plants and number of ears per plant, and in the case of soybeans, the pod counts, and they can get a much more accurate estimate of the yield by doing that. So we've talked several times in this class about how commodity markets really respond to important USDA reports, particularly the production reports that are released in conjunction with the WASDE report. And because of that, there's developed this cottage industry of private analysts or private proprietary trading shops trying to anticipate what the yield forecast would be. And the motivation for that is obvious. If you can figure out that the USDA is going to raise yield and cause prices to go down, then you can go short the day before and make money. And there's a lot of resources and effort by private parties to try to do that well. That's a tough game, though, because the level of resources that the USDA sends out to do these monthly yield estimates is quite a bit more than what any single private firm could employ. So usually at the end of the day, when we go back and look at research that evaluates the USDA estimates, they come out actually very well. And if you compare private estimates to the performance of the USDA, they typically, over the long run, can't really outperform the estimates that the USDA puts out. As difficult as it is to beat the USDA estimates for yield, there will be many cases where, whether you're in a private firm or you're trying to make investment decisions or you're trying to make speculative trading decisions, you're going to need to have an estimate of yield before or between USDA reports, and you need some technique to get your hands on where we kind of stand in terms of yields for that year. Now, absent of having a really detailed and sophisticated agronomic model that can input things like precipitation and heating degree days and have a very good understanding of the geographic dispersion of weather, you're probably going to be reliant on looking at historical data and specifically historical deviations from trend yield. And there are two main ways you can look at that. You can look at deviations in levels, that's what I've got pictured here, and percent deviations from yield, and that would be calculated instead of just taking the difference between yield and trend yield. You'd take the log difference between yield and log of trend yield, and that would represent a percentage change from the trend line. Now, the advantage to this approach is you can say to yourself, okay, this year we have 6 more inches in July than average in terms of precipitation. Let me go and find a year in the recent history and see what we ended up with in yield in that kind of weather outcome. And so looking at historical deviations from trend yield can allow you to do that kind of analysis. Now, you do have to make a decision. Are you going to use deviations from trend in levels or deviations from trend in percent? And I've plotted them both here, and you can see they have a generally similar shape, but the one that is on top is a deviation from trend in levels, and that's going to exaggerate the impacts of deviations from trend in more recent years because that yield realization line was trending upward, and the deviations were probably getting a little more volatile. At least that's what the evidence of these two graphs suggests. So in levels, it looks like 2012 was the most severe drought in recent history, but if we calculate it as percent deviation from trend, the 2012 drought was among the worst, but it was not worse than the 1988 drought.